3 years. So I'll discuss with you what I have done or what I have experienced through these 3 years. So what I've done is like I went through this application, like biosensing application using HEMT devices. So yesterday and day before yesterday, so they were talking about high power, high frequency applications of this device. So GaN is having another important feature that enables it for biosensing applications. So that is in turn the biocompatibility of the device. So this is an outline of what I'm going to present today. So I'll give a brief introduction of why GaN is required or why sensor based on GaN is required. Then I'll talk about what are the different types of sensors that are present that are already presented by some others. And then I'll talk about how I have done simulations in order to optimize the device design. Followed by that, I'll show the mathematical model that I have made for the biosensor. So simulation and modeling, these are at most essential for before going to the fabrication phase. So if we have to finally develop a product or take a device to the product development phase, we have to depend on all these three things like simulation, modeling, and fabrication in order to come out with a device design that can be taken to the product level. And after that, I'll discuss about the fabrication, like what are the steps in fabrication of a simple HEMT, like a HEMT structure that I have optimized. And then I'll say about what are the different types of HEMTs that I have fabricated, and then how these sensors or how these devices can be used in sensing applications. So for this, I'll show you not exactly the clinical trials, but how I have used or how I have used a model-based approach and a fabricated device and use them for testing the sensitivity of the device. And then I'll tell you what are the conclusions made and what can be done in the future. So introduction. So I'll not give a deep introduction about this GaN material because all of you were listening about GaN or the advantages of GaN over the past 2-3 days. So it's not necessary for me to tell you what GaN is or how it operates. But overall, I'll give a simple idea about what GaN is. GaN is a material with a very high band gap. So this wide band gap of the material makes the device suitable for high temperature applications. Chemical stabilities are high. So it's also having a piezoelectric nature and non-toxicity to the living cells or to the biocells that are present in our body. So it is the high ruggedness of this HEMT that has gained the sensor field attention to this particular device. So if we check in the market, we can find that there are a large amount of sensors. So most of the sensors are based on silicon-based devices. However, when the silicon-based biosensors are considered, these are easily attacked by chemical or bioreagents. So as we know, silicon is a material that can easily be etched by bases. So if the pH of a solution, like if a KOH or potassium hydroxide is considered. So if we keep silicon-based device in potassium hydroxide, then the sensor or the surface gets degraded or corroded. So we can't go for using reliable silicon sensors for all kinds of detections. For example, if we consider some biodetections from a body blood or something. So if a person is affected by some kind of diseases, so his body pH or blood pH can vary. So if he is having a very high pH of his blood, and if he is using a silicon-based sensor, then the silicon-based sensor may get etched away because of this particular pH in his blood itself. So we can't go for relying the silicon-based sensors. So other limitations of the silicon-based sensor are its poor ruggedness. Like it cannot be used above a particular temperature or it cannot be used in a hazardous environment. Also, when we consider the shelf life of the sensor, the shelf lives are very poor, like very few months we can use it or very few days we can use it. Similarly, if we consider the chemical stability or the thermal stability, it cannot be used above a temperature of like 300 to 400 degrees Celsius, and it cannot be used in all kinds of chemical environments. And again, when we consider a biosensor, we have to develop a sensor that is reusable. However, using silicon, such a technology has not come till date. And also the final limitation of the device is the low sensitivity. So how this low sensitivity is a limitation? This is in turn because if we go for detection of some kind of diseases such as cancers or tumors or any other kind of diseases, then we'll have to go for detecting it at a very early stage so that it can be treated well or people can be prevented from deaths. So for this, we need an early detection. So using silicon, we cannot do an early detection, but using GaN HEMTs, because of its piezoelectric nature as well as of its other advantages, we can attain early detection and reusable sensors can be made. So all these advantages of GaN HEMT is in turn because of this interesting property of 2D EG, that is two-dimensional electron gas that is present in the case of the device. So you all will be familiar with this 2D EG as Murugapandian sir in his lecture, like day before yesterday, he has explained well about how this 2D EG is formed, about the piezoelectric polarization, spontaneous polarization, and everything related to the working of the device. So here again, even when we are considering a sensor device, the working or the principle of operation of the device is again the same. The only thing is like we are using it in a different application domain, that is we are using it for sensors. So I'll be explaining how this can be used in sensing applications. So the motivation for me to do this research is like, if even today we can find we all are stuck at our homes. So this is in turn because of this pandemic, that is coronavirus. And we know that researchers all over the world, or researchers in India and in other countries, they are continuously trying to develop some test kits that can be used to detect this coronavirus. And daily we are hearing the news that we are running out of test kits. And these test kits, even if we were having those in the initial stages, we know that they were taking huge response times. Like if we give a sample today, they were giving the results after 3 or 4 days. So this was taking a lot of time. And as a result of this, we were suffering from this disease. So this is in turn because of the lack of cheap technologies that can be used to give fast responses for life-threatening diseases. So coronavirus is not just the case. There are other diseases that are already existing, such as cancers, tumors, kidney injuries, and other various diseases. Like other viruses also came and they went, like Zika virus, Nipah virus. Everything came and they went, but still we can find that there is no reliable technology that is existing using which we can detect these kinds of diseases. So HEMT device, even though it's immature these days, if it is taken to a maturity stage, then these devices can be used as a sensor for all these kinds of diseases. And if such a sensor is put forward, or if such a product can be developed, and if it is developed as a personal healthcare equipment, then the death rate by these diseases can be reduced by about 96 to 98%, and this was proved by the American Cancer Society. So right now, what are the methods that are used to find out these diseases? For example, the death rate due to the cancers and tumors are very high these days. This is in turn because of the technology that is used in the diagnosis, that is mammography or something related to that, which is a like difficult method, and we need to go to the hospital and we have to spend hours and hours there, and we have to spend a lot of money in order to do that testing. So if a person like me or you who is not having any kind of symptoms will not by ourselves go to the hospital and tell like we need to test for a cancer or a tumor. But in the early stages of most of these diseases, we can find that there will not be any kind of symptoms that is present. For example, if we consider a breast cancer or a prostate cancer, the early stages, this will be asymptomatic. So we will not be knowing that we are affected by this particular disease unless and until this spreads to the other part of the body. So when these cancers or tumors, they spread to other parts of the body, then it will start to give us pain or some other kinds of irritation. That is when we go to the hospital. But by then it will be very late. Like we would have passed the early stages, and then it will be difficult to tackle the disease. And that is the reason for most of the death due to these kinds of diseases. So how can this be reduced? So this can be reduced only if all people or all the citizens of a country, they are made to go for a bi-monthly or a tri-monthly screening, even without any kind of symptoms. Right now, this is not possible. This is because we do not have a cheap or reliable technology that can be used for it. For example, in the case of a diabetic person, he has that glucose sticks that we can use at homes. So this will be like personal healthcare equipment. So without the help of any kind of clinicians or any kind of doctors, we can also test our glucose levels. So my aim here is in order to develop a device that can be used similar to a glucose detector. So that can be used as personal healthcare equipment at our homes in order to go for a screening of all these kinds of diseases such as tumors, cancers, kidney injuries, and even these kind of viruses like coronavirus, Zika virus, etc., etc., etc. So these are the existing diagnosis techniques. For example, this is in the case of a prostate cancer. So this is an MRI scan. So this is one of the major method that is used in screening these days. But MRI scan as such, it's a very huge system. So, and this tunnel of this MRI scan, it is in turn known as the tunnel of anxiety. So people by themselves stay away from these techniques, and also it consumes a lot of energy, time, and process waste. So people will not go for an MRI scan. At least I will not go for an MRI scan if I do not have any kind of symptoms. Now, the second kind of method that is available these days is biopsy. So biopsy again has its own limitations, and it's a painful kind of method. Like no one will go for a biopsy unless and until he comes to know he is having some kind of symptoms or he is having a particular disease. And even if someone goes for a biopsy, it has been proved that biopsies can give 20% false positive results. So it depends on the place from where we are taking the tissue for the biopsy test. So sometimes we can take a tissue from some other area while the cancer is in some other area. In that case, we'll get a false positive or a false negative result. So this again has about 20% false positive rates. And it's also again a time consuming method. It will take like weeks or at least days in order to get the response or results of this. And again, this can create anxiety issues. Now, in the case of prostate cancer, the third method that is available is the digital rectal examination. So here also there are limitations. That is, here also we cannot completely go for a digital examination in order to see if we are affected by some kind of cancers or tumors because of the limitations. Like we can see only till a certain region inside our body. We can't go to the entire region. So we will not depend on DREs. And the final kind of test is the antigen-based test or the blood test or other body fluid test. So these are the tests where we detect a particular biomarker which is used for the disease detection. So for example, in the case of a prostate cancer, there is an antigen called prostate-specific antigen. So these are actually proteins that are present in the human body fluid such as blood, saliva, urine, etc. So when a person is a healthy person, there will be a very low concentration of these particular biomarkers. But when the person is affected by a particular disease, then the concentration of this biomarker will be very high. So we can use this variation in the biomarker concentration in order to find if a person is affected by a particular disease. And compared to all the other methods that are presented here, this seems to be the easiest method, and this seems to be the fastest method and an affordable method. So we are trying to develop a sample detection method or using the GaN Hemp systems. So these are the advantages of the GaN Hemp or gallium nitride material. So these are the advantages such as high band gap, high relative permittivity, high breakdown field, thermal conductivity, etc. So these were discussed yesterday and day before yesterday. So this makes the device suitable for high power, high frequency performance. And there are three basic application domains of this particular material, that is the optical devices, power devices, and the sensor devices. However, optical devices, if we check, we can find that it has already attained commercial breakthrough by 2004, and we can find there are a lot of GaN LEDs that are available in the market. When we consider the power market, it is still at the verge of breakthrough, and we know there are so many researchers around the world who are working on these power devices. And if we check the power devices that are available in the market, we can find that there are a huge lot of devices like GaN RF devices and power devices available in market. But still there is large amount of research required in the power market domain, because when we go for simulation or when we go for modeling approach, we are getting devices that can operate at a very high voltage, like 1000 kilovolt. Like yesterday, sir was talking, he was getting a breakdown voltage of above 1 kilovolt. And day before yesterday, Murugapandian sir was talking like he was getting a breakdown voltage of about 914 volt. But if we check the power device market or GaN Hemps that are available in the market, we can find that all of the devices are attaining a suboptimal breakdown. Like these devices are breaking down at a voltage of less than 100 volts. So this shows that large amount of research is necessary in order to achieve all the promises of the GaN material. So GaN as such is having a very high breakdown field of about 3 megavolt per centimeter. So this has to provide a very high breakdown field. However, when the fabrication is done, it is found that all the devices break down at a very low voltage, like maximum of 300 or 400 voltage has been seen in the case of fabricated devices. And the last domain for the GaN Hemp is the sensor market. So sensor market is not just the biosensor market. These are the market for physical, chemical, and biosensors. So in this market, we can find that if we check the GaN Hemp sensors used in this market, or the commercialization is not possible till now, because we have to develop a mature technology which is very cheap. Because currently in market, we can find that there are other competitors. There are silicon-based sensors which are very cheap. So if we have to bring GaN to that level, then we have to reduce the cost of the device, and there are so many limitations that are still existing. So a huge amount of research is required in the sensor market, and sensor devices are not highly focused, at least in India, when GaN is considered. Now this is a simple or basic history of the GaN devices. So GaN crystals were first found out in the year 1960s, and the first hemp that was designed in Fujitsu lab was in the year 1980. This was not a GaN hemp, this was an AlGaN hemp. So this was the first hemp that were developed, and this is considered to be the simplest form of HEMTs. However, we can't use a gallium arsenide based HEMT for this biosensing application because it is not a biocompatible material. Now, hemp was declared as the lowest noise device in the year 1985. So lowest noise in turn depends on the doping that is used. Like this is not a device that depends on doping use. This is a device that is based on the heterostructure. So as it is not having doping noise, as its inherent noise in the device will be very low. Again, the first GaN-AlGaN heterojunction was fabricated in the year 1991, which led to the development of this first hemp or GaN-based hemp in the year 1993. Later, this was used in microwave electronics in 1994, and in 1997, high power capability of these hemps were realized. So yesterday and day before yesterday, so you were going through the working of the hemp. So principle again is the same. There will be a wide band gap material that is aligned with a narrow band gap material. And hence there will be a conduction band bending at the heterojunction, which will be leading to a bending of the conduction band below the Fermi level at the interface, leading to a region called the 2D EG or the two-dimensional electron gas. So this is the heart of principle of operation of the device. So if we want to modulate any properties of the device, or if we want to improve the quality of a device, we have to work on engineering this 2D EG. So we can go to this by various methods, like by adding layers, by using gate engineering, by using different kind of passivation. But at the end, if we check what we are optimizing, is actually the 2D EG in the device, and it is the heart of operation of the device. Now, as I've said, HEMT sensor has a large amount of competitors in the market. So these days we can find there are a large number of silicon-based MOSFETs and ISFETs that are present in the market, but these have so many limitations. So as I've already said, these are not reliable when sensing is considered in aqueous solutions or when a high pH is considered. Similarly, MOSFETs and ISFETs, these require a reference electrode. But in our case, that is in the case of GaN HEMTs, normally it is an on device. So we do not require a reference electrode just to turn on the device. Rather, it is always an on device. So that is first advantage of HEMT over MOSFETs and ISFETs. Second advantage of HEMT is like MOSFETs and ISFETs are not reusable. Like we cannot wash the surface of the device simply by using some kind of solutions. But when HEMT sensors are considered, we can go for cleaning the surface of the sensor by using protein buffers or wash buffers. As a result, we can develop a reusable sensor. So thus the cost limitation of HEMT. So GaN HEMT is having a high cost compared to the MOSFETs and ISFETs. But when it is a reusable device, we can afford a device with a higher cost instead of going for multiple devices. So that is another advantage of HEMT. And the third advantage of HEMT is like here the output characteristics can be used in sensing. So if someone among you has studied anything related to sensors, you can find that MOSFETs and ISFETs, they rely on the subthreshold characteristics such as subthreshold voltage or subthreshold current in order to do the sensing performance or in order to evaluate the sensing performance. But when HEMT is considered, we can take the output device characteristics or output drain current as the sensing metric, or variation in output drain current can be used as a sensor output. So these are the advantages of HEMT over the MOSFETs and ISFETs. However, in order to bring this HEMT to the commercialization level, still a lot of research has to be put forward. So these are few examples of HEMT sensors in literature. Like I have included them in references, like HEMT-based biosensors. So in biosensing, they have been used for different types of cancer detection, such as prostate cancer detection, breast cancer detection, and lung cancer detection. Any cancer can be detected by using HEMT. Similarly, they can be used for detection of different types of kidney injuries, liver injuries, or any kind of injuries. And again, when we go to the HEMT-based chemical sensors, so if we check the chemical sensors in market or not in market, if we check the sensors in history, we can find that there are a lot of HEMT sensors in chemical domain. That is, they are used for pH detection, that is to find acidity or basicity of a solution. Again, we can find that people have worked on developing sensors for different gas detections, different ion detections, like they are used for cations and anion detections. And again, if we come to the physical sensor domain, these can be used for sensing any physical quantity. So any physical quantity in the sense, examples of HEMT sensors in literature are for terahertz wave detection, magnetic field detection, stress detection, pressure detection, etc. So what is the principle of operation of a sensor? So it is again same as the HEMT operating principle. So here we'll have a gate surface or a channel surface, and the channel surface will be applying a physical parameter or whatever is to be measured. So there will be a variation in the surface potential that is generated. So this will act as a potential that is applied to the device channel, and this will modulate the 2D EG that is present in the channel, and as a result of this, the characteristics or the current in the device will increase or decrease. So these are the few examples or few challenges that limits the HEMT sensor commercialization. So first one is the poor stability of surface functionalization. So as I have said, HEMT is a very stable device. So it has got high chemical and thermal stability. But when we develop a device or when we develop a sensor, we have to go for functionalizing the surface of the sensor depending upon the sensing that is to be performed. So this functionalization levels, functionalization things like chemicals that are used for this functionalization, this gets degraded easily, and hence the shelf life of the sensors gets reduced. So we have to go for stabilizing the functionalization using some kind of stabilizers. So optimization of this is still pending. So we have to work on this in order to take this HEMT to the commercialization phase. Now the second limitation is a poor resolution. So as I have said, if we have to go for an early detection, like early cancer or tumor detection, then we have to get a device with a very low detection limit. Like it has to detect like nanogram or even picogram per milliliter of that protein sample that is present in the body fluids. So in that case, we have to develop a sensor that is having a very high resolution. Now the third limitation is the high cost involved. So GaN hemp, like people working on GaN hemp will be knowing the cost issues. Like unlike the silicon technology, which is mature in nature, and there are CMOS compatible processes that are available in fabrication. When we come to the GaN hemp domain, GaN is a new material, and we don't have wafers of GaN because of the limitation that GaN is not available in huge quantities. So we have to go for growth over some foreign substrates, and from there starts the difficulties. And when we consider the overall cost of fabrication of a GaN hemp, it is very high compared to the silicon-based devices. And along with this, there is no packaging technology that is developed, which is an optimized packaging technology that can be used in the case of the GaN hemp. So again, these are the different stages of research that is required in order to take this device to the product development phase. And finally, the limitation is a multi-detection. Like till date, GaN hemp sensors are developed like a sensor is developed with focus on cancer sensing applications, like breast cancer sensing application. Another person is developing a sensor for a kidney injury sensing application. But we have to develop a sensor like a universal platform that can be used for multiple detection. Like we can't simply go for optimizing devices every day for finding sensors for different applications. So again, we have to come up with a design that can be used as a universal sensor for different applications. So what I am trying to do is like, in order to develop a sensor that can be used for any kind of application, just by modulating or modifying the surface of the device or channel surface of the device. So I'm still doing research in this domain, and I have come up with some results. However, I have not taken the device to the final product development stage. We are still working on that. So this is where I started my work. So anything, if you have to go for a fabrication, you have to come up with an optimized device design. And to come up with an optimized device design, you have to depend on some kind of simulation or modeling tools. Because GaN, as I've said, is a very costly material. So we can't simply go for fabricating any structures and telling like this is operating better than that one. And if we fabricate another kind of device, it will give further better performance. So what we can do is like we can firstly go for optimizing the device design using simulation. So this simulation I have done on Silvaco Atlas TCAD. So I began with a simple GaN AlGaN heterojunction that is used was on a silicon substrate. So here I have grown this, I have simulated this device design for aluminium mole fraction 0.3 and gallium 0.7. So I went for optimizing each of these individual parameters in the case of the device. So first thing that I tried to optimize was this aluminium mole fraction. So what is the optimal mole fraction of aluminium that is used in a device design? So this depends upon the application. However, I found that as I was increasing this aluminium mole fraction in AlGaN, it was increasing the 2DEG or mobility in the device. That is 2D interface charge density in the device. But it was also seen that this is a ternary compound semiconductor material. So that is aluminium, gallium, and nitrogen are present in this. So as I was increasing the concentration of this aluminium above 0.4 or something, I was finding that it was leading to a large amount of scattering in the device. So I couldn't go for simply increasing the concentration of aluminium. So it is said that we are going to develop a device. We have to go for using an optimum aluminium mole fraction ranging from 0.2 to 0.4. So it will be best if we can choose an aluminium mole fraction from 0.2 to 0.3. So we can't go for increasing this. So how else can we increase the 2DG density at the interface? So next method that I adopted is like I included an aluminum nitride interlayer of 1 nanometer here. So when an aluminum nitride interlayer is added, it increased the 2DG density and also it reduced the disorder scattering due to the ternary semiconductor material that is AlGaN present. So this aluminum nitride spacer layer, it is having two functions. That is first of all in order to increase the conduction band offset at the interface, thereby increasing the 2DEG. And second one is in order to enhance or in order to reduce the disorder scattering, so defects in the case of the device. So after that, I again went for adding another layer, that is a nucleation layer. So when the nucleation layer was added, again it was found that the device operation or device performance increases. This is because here we are growing this GaN on silicon substrate. So in my work, I have focused on silicon substrate. This is because I'm working on a sensor. So sensors have to be very cheap. So we can't simply go for using a silicon carbide substrate or a diamond substrate. This is because these are very costly substrates. So we cannot go for a sensor based on those substrates, even though we know that they will be giving better performance compared to our device. So we have to focus on many things when we are going to develop a device. So keeping in mind to develop a cheap sensor technology, I went for choosing a silicon substrate. But then this limitation came, like I was using this substrate as silicon, then I had to grow this GaN on silicon. So here there is a huge lattice mismatch between the substrate and the GaN layer. So when we grow this directly on top of each other, then there will be lattice mismatch and hence defects will be huge. So in order to reduce this lattice mismatch, I used an aluminum nitride nucleation layer here. So this is having a lattice constant that is lying between that of the substrate and the GaN layer, and hence the device performance improved. So now I'll summarize the different device designs that I've used. I'll not be explaining why all this, why and how this affected the performance of the device. So this is what I began with. Like I used a GaN AlGaN on a substrate. Then I included an aluminum nitride spacer layer into it. Then I included an aluminum nitride nucleation. Then I used an aluminum gallium nitride transition scheme. This is again for the lattice mismatch reduction. Then I added a GaN cap layer of about 2 nanometer onto the surface. This is because here traps will be introduced at the gate side edge of the drain side edge of the gate, and there will be some electric field peaks that will be formed at this region. So here, in order to overcome this defects, or in order to get a better performance, I was using a GaN cap layer. So how this defects is formed is in turn because of the 2D that is present at the interface. So when a 2D it's a negatively charged layer that is present. So counter ions will be accumulating at the positive at the surface of the device, and this will be leading to unwanted electric fields that causes issues in the device. So this can be removed or reduced to a certain level by using a GaN cap layer. So after this, we have also added some passivation layers. Like we have worked with double passivation, single passivation, and passivation using a silicon nitride layer, aluminum nitride layer, silicon dioxide layer, a combination of aluminum nitride, silicon nitride, etc. in order to get better performance and overcome current collapse that was occurring in the device. And finally, we also worked with an oxide-based device, that is a MOS HEMT, metal oxide semiconductor HEMTs. So here, like the MOSFET, here it will be having a dielectric modulated gate. So here again, we have tried to optimize the thickness of the gate oxide as well as the material of the gate oxide. So we have worked with 3 basic gate oxides, that is Al2O3, HFO2 and SiO2. And we found that Al2O3 gives the best performance when the devices are fabricated for sensing applications. So the device operation, so I'm not going to explain this in detail. So this is the band diagram when this aluminum nitride was incorporated. So here conduction band offset that increases when this aluminum nitride is introduced at the hetero interface. So this is AlGaN with a band gap of 3.96 and GaN with a band gap of 3.4. When ALN with a very high band gap of around 7 or 8 is introduced in between, it is found that there will be a huge conduction band offset that is created. So this is the increase in the conduction band offset, that is delta EC effective. So this is modeled by this equation. So this equation is of importance. This is because the entire performance of the device depends upon this particular equation. So using this, we can model the 2DEG in the device. That is, the 2DEG in the device is given by the term NS. This is the interface 2DEG density, and this depends upon the delta EC effective or the conduction band offset. So if we have a higher conduction band offset, it is found that 2DEG density increases. This is in turn because the conduction band bending into the Fermi level increases. And this diagram here at the bottom, it shows the interface charge with and without the aluminum nitride interlayer. So when the aluminum nitride interlayer was introduced, it is found that we are getting a higher interface density compared to the structure without the aluminum nitride interlayer. So these are few characteristics to show how the device characteristics improves when we go for using some interlayers or passivation schemes or something like that. So in every case, we can find that we are getting improvement. So this is one way in order to optimize the device through simulations, like to study the characteristics. So these are the characteristics of the device for different domains, like drain current is plotted here, transconductance, cutoff frequency, and the breakdown voltages. So here, when we consider a sensing domain, the important parameters will be drain current and transconductance. While when we consider a high power or high frequency domain, again the important parameters will be not just drain current and transconductance. We'll also have to work with the breakdown voltage and the cutoff frequency in the device. So these are different parameters. In my work, I had to focus on this drain current and transconductance, that is GM of the device, in order to give a better sensing device. So this is a comparison like with the existing devices, just to show that the optimized device design that we are using is not a very bad design, like it is giving comparatively good results or comparable results with the proposed devices for even high power, high frequency applications. So here we were attaining a high on current of 2.63 ampere per millimeter with a high transconductance of 405 millisiemens per millimeter. So these both were the important parameters for us taking it from a sensing point of view. However, the device was also giving a very high breakdown voltage of 539 volt and an output power density of 17.69 watt per millimeter. Now, so this is how the simulation was used. So I've used simulation in order to add layers or add performance boosters into the device in order to optimize the device design. However, even if we go for simulation and state like we are getting a highly performing device and this is giving that results, and if we are trying to prove that to somebody, then they'll ask like, how can you validate the simulation? Or like simulation is just using models. You are not modeling for any kind of defects or anything in the device. So we have to go for depending upon, or we have to go for using some theoretical approach or modeling approach in order to validate the simulations that we are doing. So for this, I have used an analytical model, or I have developed an analytical model for a particular sensor, that is a hemp-based breast cancer sensor. So this is the analytical model. So why this breast cancer detection? So I was interested in this topic because it was found that it is a leading cause for death in females. And it is found that there are a very large number of females that are affected by this particular device, and there are no proper sensors to find it. So the only diagnosis method that is available is mammography. However, people are afraid of mammography as it uses radiations and as it is very time consuming and very expensive. So again, I started working with this particular detection, that is breast cancer detection. So for breast cancer, there's a biomarker that is CERBP2, that is a protein, that's a transmembrane glycoprotein that is present in human blood, human saliva, as well as human urine. But the concentrations will be different in different body fluids. So we have simulated some device structure. So we tried to come out with an equation or with a theoretical model or an analytical model for that particular device in order to study its sensing behavior or how it will be acting as a sensor. So these are few models that are existing in literature. So if we go to a high frequency, high power domain, or if we go for some other domains such as optical domain where large amount of research is already done, we can find that there are a large amount of models that are existing, and that is what eases the fabrication process or the product development process, because they use the models and come with a design and then they fabricate it. But when we consider this biosensing domain or sensing domain, we can find that there are no models that are present, or rather there were only two models that was present when I was checking this for the first time. And the first model is a model by Kandalwal et al, and he proposed a model that was considering a uniform Fermi potential. But this is not true when the gate voltage is increased above 2 volt. And another limitation of this model was that it was not accounting for the impact of drain bias. So when a sensor is considered, as the drain bias increases, the sensitivity increases. But this model is having a limitation that they cannot account for this increase or decrease in sensitivity with the drain bias. So that was the limitations that I found for this model. Now another model was proposed by Igletu et al. So this was a very complicated paper. I went through it, but I didn't understand a word of it. So this limitation of the paper that I found out is it's very complex. So normal people like us can't use it. So its applicability is limited. Now, next is the model that I have developed. So I've used the normal drain current equation, that is ID is equal to Q NS into Z into V of X. So anyone who is working on HEMT will be familiar with this particular equation, where Q is the electron charge, NS is the 2DG density, Z is the thickness or the channel width of the device, and V of X is the channel potential at a length X in the channel. So this is a basic or simple HEMT equation. And previously we have found out an equation for delta EC effective, and using that we have developed an equation for this NS, that is 2DG density in the device. So now we are expanding this equation based on the terms that we have already used. That is, on expanding we'll get such a big equation, but this is a simple ID equation that is expanded using all the terms that are involved. So it depends on all these parameters. Now for sensor model, what happens with sensing is we'll have a gate electrode. So in our case, we have a gold gate electrode. So on the surface of the gate electrode, we'll be using some kind of functionalization. Functionalization in the sense is just similar to a biomolecular linker that will be attached to the gate surface, and then we'll be introducing the sample onto the surface. So when the sample that is containing the target biomolecule is introduced, there will be antigen antibody interaction. So we'll be coating the gate electrode with this antibody, and we are introducing the antigen. So there will be antigen antibody interaction or antigen antibody linkage occurs on the surface. So this will lead to an effective surface potential generation. So when a surface potential is generated on the gate electrode, then it is just similar to a VGS or gate potential that is applied through an external bias. But here the difference is here the potential that is generated will be very small. So our aim here through the model is in order to find out what is the potential that occurs at the gate surface due to this biomolecular immobilization. So when this immobilization occurs, it gets capacitively coupled to the channel, and this is a 2DG present in the channel, and the 2DG gets modulated. So here we have written the equation for the variation in 2D EG, that is delta NS, which is equal to this term in the equation. So we have used a linear kind of modeling. So we based on VGS increase and decrease on bioimmobilization, and we have derived an equation for ID plus delta ID. So we have that ID equation. ID is Q into NS into Z into V of X. Now here ID plus delta ID will become Q into NS plus delta NS plus into Z into V of X. So this is again the expansion for that particular equation, and this will be the sensor current or the output current when the bioimmobilization occurs on the sensor surface. Now for validation of the model, we have used a simulation. So we have already simulated the device design. So we have compared the results from the simulation and this theoretical model. So in simulation, what we have done is like we have found out the equivalent interface charge due to this particular biomarker, and we introduced it as an interface charge to the surface of the device by defining an intrinsic semiconductor. And in the case of model, we have found out the effective surface potential due to this biomarker and introduced it as a gate bias. Now I'll explain how this biomarker model or how the effective voltage or charge due to the biomarker is deduced. So this is the biomarker for breast cancer detection, that is the CERB2 or the breast cancer biomarker. So its value will be like 25 to 30% expanded or increased when a person is affected by this particular kind of cancer. So this is the concentration in healthy and diseased person. So this is a clinically relevant concentration in saliva of the patient. Like in a healthy person, the concentration will be 4 to 6 microgram per milliliter, while it will be increasing to 9 to 13 microgram per milliliter if a person is affected by this cancer. So our aim is in order to find out this concentration of this particular biomarker and in order to tell like whether the person is affected or what stage he is affected with this particular cancer. So similarly, in the case of the blood of the person, here we can find that the concentration should be 60 to 90 microgram per milliliter, which can increase to 140 to 210 microgram per milliliter when the person is affected by cancer. So if we can come to know about the level of this particular biomarker in his body fluids, his or her body fluids like saliva or serum, then we can go for developing these sensors. So advantage of this HEMT-based sensor is like we can develop label-free bio detectors, and we can go for sensing even from saliva of the patient. So when saliva of the patient is used for detection, it's like we needn't even use a invasive kind of method. Like we needn't go for injecting a syringe into our body. We can just use the saliva in order to see if we are affected by this particular disease. So this is how the charge due to this biomarker is found out. So if we know the concentration of biomarker, that is a clinically relevant concentration, and the charge on the biomarker of interest. So in the case of CERB2, it's a protein which is having an effective charge which is in negative range. And using the Avogadro number, we can find out the effective concentration of this particular biomarker. And we can simply reduce the effective charge due to this particular biomarker in required quantities. And then using that equivalent charge, we can come out with the equivalent DC bias that is to be applied to the gate in the case of the model that is developed. Like when the immobilization occurs on the surface, there will be X number of charges that will be present on the surface. So the total charge or total voltage. Okay. So the total voltage due to this X number of biomarker charges or biomarker molecules will be given as X into E by Q. E by Q is actually the electric field equivalent in HEMT or GaN devices, and this will be equivalent to the voltage due to an individual biomarker. So if we can know the total number of biomarkers that are present on the surface, we can find out the equivalent voltage that is to be applied on the device gate in order to do a physical detection kind of thing in the model itself. So these are few sensing currents that I've obtained. So this is just showed in order to show that we are attaining good sensitivity using the devices, so that the devices can be used for like early detection. Like in the case of a healthy person, this red line and the black line, this is for a healthy person, while when a deceased person sample is considered, the current in the device or the sensing current will be increasing to a very high levels. So just by using the output current or just by noting the output current levels in the HEMT, we can say that the person is affected by a particular disease or not. So this testing methodology is very simple. Like response time also will be very simple. So as this very fast response will be produced as this HEMTs are high frequency devices. So within milliseconds or less than that, we can get response like whether a person is affected by cancer or whether he is a healthy person, just by seeing the output currents in the device using any device like an ammeter or anything like that. Now, channel conductance variation. Again, that was one of the parameters of the device that we use for sensing analysis. Again, channel conductance in the device can be used for sensitivity analysis. It's just to show that how the channel conductance of the device varies with this bioimmobilization. So it's again a comparison between the simulation and the model. So we have used both everywhere in order to validate that we are not going in the wrong path. Like simulation is matching with the model and model is matching with the simulation results. So thus we have validated this work. So if anyone wants details about this work is published in my paper in IEEE Sensors Journal last year. So you can go through it. So here I have used different parameters of the device like drain current, transconductance, and drain conductance in the device in order to see how the sensor performs. So these things were done prior to the fabrication. And then we analyze the sensitivity of the device. Sensitivity is like how much current in the device will be varying for unit increase in concentration of that biomarker molecule. So we know that the healthy range of this biomarker molecule is 4 to 6 microgram per milliliter, and the disease range is from 9 to 13 microgram per milliliter. So if we can detect it at a stage like 7 or 6 microgram per milliliter, then it's like we can come for an early detection. Like we can find that this particular biomarker or protein is increasing. So maybe this person can get affected by this particular cancer, and a continuous screening can be done from that level. So this is how early detection can be made possible. And in the case of this particular device, we were getting a high variation in on current, and the on current sensitivity was found to be 2.5 milliamperes per unit increase in concentration of CRB2 in microgram per milliliter. Again, we also studied how the device varies, like how the dimension of the device affects the sensitivity. So these are again optimization techniques before going for fabrication, like what is the length or gate length that is used to get a good sensor. So if we are going for a high power domain or a high frequency domain, so there the people focus on scaling down or miniaturization. So they have to follow different roadmaps like ITRS roadmaps, and they have to get very high currents, very high frequencies, etc. But in our case, like being a sensing domain person, I don't focus on miniaturization. I focus on enhancing the sensitivity of the device. So for enhancing the sensitivity of the device, we can't go for miniaturization, or we can't go for using minimum gate length, because as I said, it is on the gate that we introduce the biomolecules. So if we have to introduce something on a gate, we need a larger area of the gate so that larger amount of molecules can be introduced and the sensing can be done in a very good level. So for this, I had studied the impact of gate length on current and the sensing current, and it was found that when the device gate length is increased, the sensitivity was decreasing. This is in turn because transconductance decreases as the channel length increases. However, it was found that even with a 5 nanometer gate or 5 micrometer gate, we were attaining good sensitivities of about 0.72 milliamperes. So this is simply a discussion on what we have done and what is the sensitivity we are obtaining. But the model we have developed is having a limitation that we don't account for the discreteness of the unit charge or the biocharge that is present. So we consider the charge to be a uniform sheet charge. Now I'll discuss about the fabrication process. So we have optimized our device design using simulation as well as modeling. So this is one of the final device design that we have fabricated. So this fabrication details I'll be explaining. So these are the different steps that I use in fabrication. So first step in any fabrication is an MOCVD or MBE based growth, because we need a GaN AlGaN or whatever material stack on a foreign substrate. So for growth of this, we have to go for MOCVD, that is metal oxide, organic chemical vapor deposition, or we have to go for an MBE process. So these are two main processes that is used for the stack growth for this hemp stack. And then we have to go for an ohmic source and drain deposition. That is a source and the drain here is having metal stacks, titanium, aluminum, nickel, gold with thicknesses 20, 120, 30 and 40 nanometer. Then we have to go for Mesa Isolation. So Mesa Isolation is like on a single wafer, we will be fabricating multiple devices. So the one device will be having some leakages with a neighboring device. So we have to eliminate this process. So for this, we have to isolate individual devices from each other. So for this, what we do is like here the substrate is still the GaN material. So we etch on the sides of the substrate, and we'll be etching like 200 nanometer of the substrate using dry etching in order to form this Mesa Isolation. And after that, we go for passivation. So in this structure, if you check, you can see there is a double passivation that is used. It is having a silicon nitride passivation of 100 nanometer and Al2O3 passivation of 10 nanometer. So we have used the double passivation scheme. And then we went for the gate oxide deposition. So we etched here for gate oxide deposition. We have deposited a 10 nanometer Al2O3, and then we ground the nickel gold stack for the gate layer, and finally we opened the pads for the titanium aluminum nickel gold source and drain stack. Excuse me?
You can continue. You can continue, please.
Okay. So this is a flow for the fabrication process. Like we have the substrate that is, and we have the materials drawn on the substrate. Then we deposit the source in the drain contacts. Then we do the Mesa isolation. Then we passivate the device and finally go for the gate metallization and gate oxide deposition. So this was the first step, that is MOCVD growth. So MOCVD growth was done using Extron CCS MOCVD reactor using different precursors. And MOCVD growth, we have grown the device on a silicon substrate using performance boosters such as aluminum nitride interlayer. We have grown all these 4 transition scheme layers. Then we have grown a GaN layer with 1.05 micrometer thickness. Then this spacer layer of 1 nanometer. And finally, we have also grown this GaN cap layer. So this is the first step for the hemp stack growth. And after the hemp stack growth, next comes the patterning. So stack growth is a simple process. We have to simply go for continuous deposition on the surface of the substrate. So that doesn't require any kind of patterning or lithography. Now next we have to go for patterning. Pattern deposition of the source and the drain contact. So here comes the importance of the masking and patterning. So in our case here we have a 5-layer mask system. So this is the mask that I have used. So whenever a person is thinking from the fabrication point of view, he has to look on the device from the top side of the device. So in the case of simulation guys, they will be focusing on the device from the side view, like cross section view will be checked, like what is the thicknesses of the layers and all. But when a mask is to be created or when a patterning is to be done, then we have to see from the top side of the device. So when we check a hemp from the top side, it will look somewhat like this. So this is the source and this is the drain. And in between we'll have the gate, and this one is a gate pad, that is an ash color pad in the side. And this is how a fabricated device will look. So this is a final view of the fabricated device using an optical microscope. So here we have used a 5-layer masking scheme. So mask 1 was for the ohmic source and drain deposition. Mask 2 is for device isolations. Mask 3 is for etching of the passivation scheme. Mask 4 is for gate metal deposition and gate oxide deposition. And mask 5 is for source and drain pad openings. So in our entire process, we have used only optical lithography. So optical lithography is used when your feature sizes are above 1 micrometer. So if we have to go for a channel length of less than 1 micrometer, that is if we have to go for developing devices with channel lengths in few nanometers, then you have to go for E-beam lithography instead of optical lithography. However, in my device, as I'm focusing on sensing application, I was using only optical lithographies. So this is how an optical lithography looks like. So this is an MJB4 aligner that is used in optical lithography. And at the center in figure B, this is the wafer, like wafer with the epitaxial stack that is grown on it. So this is a wafer on silicon substrate with all the GaN stacks that is grown, including performance boosters. So in my entire fabrication, I have used only optical lithography, and I have used the positive PR AZ5214E. And these are the dosages. Like you'll know the details once any one of you get into the fabrication. Till then, these are like you can go for using any kind of PR. You can go for using any kind of mask and anything like that. Now this is how this patterning happens. So this was the first step, that is we have the substrate, and substrate in the sense this is a hemp epitaxial stack that is grown on silicon substrate. Now what we do is like we first of all deposit the photoresist on the substrate surface. Then we introduce the mask. So mask will be having opening at these 2 areas where we have to deposit the source and the drain. And then the photoresist will be exposed to UV. So when we expose it to UV, then these areas, like wherever the mask is open, the photoresist will become very light, or it will become removable in nature. And as we drop it in and develop a solution, so we'll get a pattern like this. Like PR will be present at these 3 regions, and there will be openings in between. So this is where we are going to deposit the source and the drain regions. So in these 2 openings, with the PR remaining on the other surface, we'll be depositing the source and the drain. So this is how the thing will look after the deposition. So this is a view from the optical microscope. So the first figure here, it is surface of the wafer after patterning. Like here we can see 2 windows are open. So these 2 windows are actually window opening for the source and drain deposition. And here on the entire region, there is a PR deposited. Like here the PR is acting as a mask. And now we will be introducing this wafer to the E-beam evaporation chamber. So in the E-beam evaporation chamber, we'll be depositing that stack of titanium, aluminum, nickel, gold for source and drain, or whatever materials you want to deposit. So now the wafer will look something like this. So here in the windows also it get deposited, and in the surrounding regions also the metal is deposited. But the difference is like here in the source and drain regions, it is directly deposited on the surface of the wafer, and in the other regions, it is deposited on the surface of the photoresist. Now in the next phase, what we do is like we have to go for removing this gold or metal layers from the remaining area in the wafer, and we have to let it remain on these two surfaces. So this is again done by sonication. Like ultrasonication is done. So we use a frequency and we keep it in a solution of acetone, and we use sound waves. So when sound waves is used at a particular frequency, we can find that the PR that is present here gets removed from the surface along with the metal that is on top of it. So the final device structure will look something like this. So here we have the source and the drain contacts that are present here, but from the other entire area, we can find that the PR along with the metal gets removed. And after the deposition, we just check the thickness of the layer deposited. For this, there is a device called the DECTAC profiler. So it's a profiler that use a cantilever kind of thing in order to check what is the thickness of the contact that is deposited. So this is the contact measurement characteristics. So here we can find that this will be the substrate surface and this will be the contact. So here we were expecting a 210 nanometer contact, but we were getting a contact of thickness about 195 nanometers. So this is the sonication, that is after the deposition, this is how the wafer will look like. So over the entire area, we can find that gold is covering the entire patterns in the device. So in sonication, we use sound waves, and this is how the sonication is done. So here we can find that the patterning is coming visible. So here this is a wafer, this is a 2-inch wafer that I have used, and I have fabricated around 2000 devices on a 2-inch wafer. So for the sonication, we have used an acetone IPA solution, and by this, we complete the second process in fabrication, that is the source and drain depositions. Now, after this, we have to go for Mesa Isolation. So, Mesa Isolation, as I said, is used to isolate the individual devices. So, these are the devices on die. So, on the substrate or on the surface of the substrate, we will have multiple devices. For example, let us consider this device, first and second devices in the first row. So, here we can find that this is a source and this is a drain, and here this is a source and this is a drain. So when we consider the leakage currents, so channel is actually formed between the source and the drain region. So current has to flow from source to the drain. But some current can flow from the source of one device or drain of one device to the source of the other device. So this has to be eliminated. So for this, we have to remove all the path that is existing between these two areas. So for this, what we do is like we remove GaN or materials that is present here. So we do a 200 nanometer etching. So we etch this area of the epitaxial stack, like 200 nanometer etching is done in order to achieve the Mesa isolation. And after the Mesa isolation, we go for a device passivation. So for device passivation, again, we have multiple methods that are available. We have used a PECVD or plasma enhanced chemical vapor deposition for silicon nitride deposition. And we have deposited around 100 nanometer silicon nitride. So there are many other methods that can be used like LPCVD, but when you choose this method, there are many things that you have to take care. Like if we have an aluminum layer in the gate stack, aluminum is having a very low melting point. Like it will melt around above a temperature of like 350-400 degrees Celsius. So if we have to go for LPCVD, temperatures will be very high, like 700 to 800 degrees Celsius. So we can't go for simply using a method for fabrication. We have to check on what our device is, what are the materials that I use, and what method is to be used to get high quality deposition. So in our device, we have used a passivation using PECVD because PECVD operates at a lower temperature compared to LPCVD. And after the passivation deposition, now we again use the mask for gate patterning. So we etched away a portion of the passivation layer again using optical lithography, and we developed a trench like this, and then we deposited the gate oxide and the gate metal. So after the gate etching or the passivation etching and gate deposition, the device will look like this at the bottom figure. So this is a pattern of the HEMT device. So this is a source, this is a drain, and in the center you can find there is a very small gate that is present. So after this, now we come to the final step in the device fabrication, that is we have to go for metallization. So for this, we deposit a gate pad, we extend the pad to the outer side of the device so that we can easily attend connections. And then we go for the pad openings for the source and the drain. So here we have used the gate oxide. So gate oxide, we have used Al2O3 as a gate oxide, and we have deposited it using atomic layer deposition. So I think everyone is familiar with how an atomic layer deposition or how a PECVD is done. So these are all basic things. And now how the devices can be used as sensors. So first of all, we have tried the sensing for pH detection. So for pH detection, we just do not need any other extra setups. We just need a HEMT device. And we have some buffer capsules. These are the pH buffer capsules. These are commercially available for like 70-80 rupees. So we bought 3 buffer capsules, that is for pH equal to 4, 7 and 9.2. That is for representing an acidic solution, a basic solution as well as a neutral solution. Now we have this device with the source, gate and the drain. So we introduce this pH solution onto the surface of the device. So you can use a gated or a gateless device for this. Even when Al2O3 surface is present, it will give higher sensitivity. So we have attached the device to an Agilent parameter analyzer. So if we see in the figure A, this is an Agilent parameter analyzer. So what is an Agilent parameter analyzer? It is just a DC measuring setup. So here you can see in the figure there are some probes that are present, like needle-like probes are present. So these probes are having an end that is just few micrometers. So using these micrometers, we are pointing it or we are attaching it to the source, drain and gate of the device. So usually this comes as a 2 probe setup or a 4 probe setup. So I use a 4 probe setup and I use this attachments. Like I attach the 3 probes of the system, source, drain and the gate, and then I measure the characteristics of the device. And for pH measurements, we have kept the gate as a floating gate. We have not applied any voltage on the gate. We have connected one probe to the source and the other to the drain, and then we introduce a buffer solution or the pH solution onto the device channel, and we analyze the sensitivity of the device. So how this pH solution detection can be used in biosensing application? So pH of the solutions has high dependence on a person whether he is affected by cancers or tumors. For example, if we consider the blood pH of a normal human being, he'll be having a blood pH in the level 7. Hello?
Please continue.
Okay. In the case of a healthy human being, his body pH or blood pH will be varying from the level 7.35 to 7.45. So if it is more acidic, it will be an indication that he is having some kind of diseases such as tumors or cancers. Similarly, if it is very basic, it is again an indicator of some other diseases. So pH level detection can be used in various kinds of detections. Similarly, in case of food industry or in the case of heavy metal industry, pH detection plays a very important role. So pH detection is at most essential, and to develop such a sensor in rugged that can operate in rugged atmosphere is also important. For example, if we have to detect the quality of a concrete wall or a concrete brick or something like that, we have to go for a sensor. So in that case, we can't go for using a silicon-based sensor because concrete is having a basic pH. So concrete. So now I'll detail on few other varieties of HEMTs that we have fabricated. So here you can see 2 structures. So one is a normal linear HEMT, you having a source, drain and a gate in between. And second figure you can see is a circular HEMT. So yesterday he was discussing about a vertical HEMT. So this is some other topology of a HEMT. Like here you'll have a central cylindrical source, and then you'll have a ring gate and a circular drain that is present. So this is another topology that can be used. So this is again used in high frequency, high power applications, and in sensing applications also it was found that when this kind of a sensor is used, it will give higher sensitivity. So higher sensitivity is in turn because here we will get a greater area, because here the gate is a circular gate or a ring shaped gate. So we can introduce a biomolecule or we can introduce a pH solution over the entire ring area. So here in the case of a normal HEMT, we have a simple or a normal gate. As a result of this, we have a limited area for functionalization or application of the biomarker. So as the increase in area of this occurs in a circular device, we can get higher sensitivity in the case of a CMOS HEMT. So these are again some characteristics of the CMOS HEMT. So we can get higher conductance as well as higher conductance to current ratio when considered from the sensing point of view, even when the normal characteristics of circular HEMTs are poorer compared to the linear HEMT. So if someone is focusing on sensing application, using of a circular based HEMT can give better results compared to a linear device. So these are the results from those devices. Like we are getting high sensitivities. So here we were getting high sensitivity of about 1.74 milliamperes per pH, which is the highest ever found sensitivity for pH solution till date. And in the case of the linear HEMT, we were attaining only sensitivity of about 1.52 milliamperes. So using a circular device, we are getting higher sensitivity. So what I want to tell is like simply by modifying the gate or modifying the device design, we can go for getting a better device design or we can get a higher sensitivity in the case of this particular device. Now, what are the different types of sensing that can be done? So these are a few examples of the different HEMT-based sensors that we have tried. Like we have used it for sensing glucose, that is diabetes detection, prostate cancer detection, breast cancer detection, kidney injury detection, and transplant rejection detection. So we have not done real-time testing for these detections, that is still pending, and we are planning to do that. What we have done till now is by using the fabricated device and using the model in order to find out the sensitivity of the devices. So this is how the process is done. So if we check the flow diagram, so the physical sensing mechanism is like you have to go for functionalizing the sensing area, and then we have to introduce the biosample and analyze the device sensitivity. What I have done is like I have used a charge direction based method, which I have already discussed in the analytical model, and using that I found out the effective gate voltage to be applied when a particular biomarker is introduced onto the surface, and applied it into the device gate and analyze the sensitivity of the device. So I've done this experiment for 5 different diseases, which seem to be the most important diseases or most spreading diseases that are causing or that are increasing the mortality rate daily. So I've tried for these 5 diseases, that is breast cancer detection, glucose detection, transplant rejection, prostate specific cancer, and kidney injury detections. And this is a charge direction model. So if we know, like, this model is not just limited to all these 5 applications, we can use the model for any application. We can find the sensitivity of the device using a MATLAB tool itself. So here what we can do is like we have to know the charge on that particular biomarker of interest. We must know the quantity or concentration of that particular biomarker, and then we should also know the quantity of the solution that we are planning to introduce onto the surface of the device. So if we know these 3 parameters, then we can easily evaluate the effective charge of the biomarker and effective voltage when this biomarker mobilization occurs onto the device channel surface or gate surface. So this is how the interface charge detection is done for different biomarkers. So for glucose oxidase enzyme, it is found that in the case of a healthy person, it is 0.4 millimole per liter in his exhaled breath condensate. This can increase to about 2.04 to 4 millimole per liter when the person is deceased or person is affected by diabetes. So similarly, we have I have found out the levels of different diseases and different biomarker concentrations. Then I evaluated the effective charges and found out the interface charges. So these are some things that anyone can do. Like they can just simply focus on any kind of biomarker or any kind of disease that they have to detect. They can find out the effective concentration due to biomarkers and find out the effective charge and apply to the device gate either in Silvaco Headless or in MATLAB, and they can claim that the device, if fabricated, can give this levels of sensitivities. So again, this model was validated. So for validation, we have actually done real-time pH detection. So using this model and the pH detection results from real-time pH detection, we compared both of this, and we were attaining or we were achieving good, like both of them were matching with each other, which proves that the model that we have developed is a realistic model rather than a simple simulation model. So this is a comparison between the model and the experiment result for pH detection. Now this is a measurement setup again. So it is an Agilent parameter analyzer that is used for DC characterization of the device. So we have worked only with the DC characteristics of the device by plotting the output drain current of the device. So here you can see this is how the probes of the device are connected. So this is a source, drain, and the gate of the device. So here this is a 3 probes of the DC parameter analyzer. This is a chuck of the device analyzer. So in the case of a DC analyzer, you can find that this is a chuck that can be heated. Like temperature analysis can also be done using the chuck. So here we have loaded the wafer on the surface. We have introduced the probes onto the source and the drain of the device. And then we checked the device sensitivity by applying the gate voltage. So here you can see this is a wafer that is loaded onto the chuck. So this wafer is having approximately 1000 devices on the surface of it. So for developing these devices or patterning these devices, we have developed the mask using the tool Clevin. Clevin is a layout designing tool or layout development tool that I have used for developing these masks. Now, this is the first detection that I was interested in, that is a blood glucose detection. So this is one of the detection that can be easily done using the HEMT devices, because this biomarker is a positively charged biomarker that is having a large concentration of 2.4 to 2.04 to 4 millimole per liter when a person is affected by diabetics, and it will be having a very low concentration of less than 0.4 millimole per liter when he is a healthy person. So using this, we found out the effective charge due to this biomarker and then introduced to the device gate and check the sensitivity of the device. So surface modulation that is required here is we have to go for growing some zinc oxide nanorods on the gate surface or the channel surface of the device, so that this sensing can be made more easily, or sensing can be further increased. So again, this is the sensitivity for GOX detection. So if you want all these details, you can check my paper in IEEE Transactions on Nanotechnology. So there is a paper called Charge Direction Based Approach for Detection. So in that paper, I have detailed all these things. So I'm not going into details of all this. Now again, for breast cancer detection. So in the breast cancer detection also, if this HEMT based sensor comes into market, it can be claimed that 98% of the death rate in women can be reduced by this particular sensor. So again, this sensing can be made using a non-invasive technique, like it can be sensed from the saliva of the patient itself. So here for this, we have this particular biomarker CRB2 with a molecular mass of 68.6 kilodalton. And its concentration will be high, like 9 to 13 microgram per milliliter in the case of a diseased person, which will be very low, like 4 to 6 in the case of a healthy person. Here also we can go for finding out the effective interface charge and effective voltage due to this particular biomarker due to immobilization and applied to the device kit to study, make the analysis. So this is again analysis due to the CRB2 biomarker, and in the case of our device that we have optimized, we were getting very high sensitivities, like compared to the existing devices, we were getting a high sensitivity of about 0.054 milliampere per unit increase in concentration of this particular biomarker. Similarly, we have worked with transplant rejection detection. This is using the biomarker monokine-induced gamma interferon. So it's having a very high molecular mass of 11.7 kilodalton, and in disease, it will be having a very high concentration of 10 to 400 nanogram per milliliter. Again, we have used the same method, and this is also a leading cause of death in human beings. Like it is found that death rate can be reduced by about 99.9% if this can be detected at an early stage, at the time of transplant rejection itself. So this is again another sensor that can be very helpful if developed. So this is how MIG sensitivity. So this is the interface of the device. So MIG again is a negatively charged biomarker. So as MIG gets immobilized on the device channel surface, the 2D EG will be bending up, like the 2D EG density decreases. That is, the device drain current decreases when this biomarker is introduced. So this negatively charged biomarker can be evaluated, or quantity of this biomarker can be evaluated by the effective decrease in the drain current in the case of the device. Similarly, we have worked with prostate cancer detection. So prostate cancer is again the leading cause of death in males, and it is found that one in every 7 humans or males will be affected by this particular cancer at some point in their life. So everyone need to go for testing of this particular cancer, but this mortality rate is not high compared as the lung cancer. So lung cancer it's just below the lung cancer, and it is considered to be the heaviest cause of death in American males. So again, for this also sensor development is an utmost heavy requirement. So here again, GaN Hemp stands as a promising candidate for detection of this prostate cancer. So here also we have checked our sensitivity. So we were again getting higher sensitivities of about 0.91 milliampere per nanogram per milliliter increase in the concentration of this particular biomarker. Again, we have tested it for kidney injuries also. So kidney injury also, we can find that complications increases as we move to the heavier levels of injuries. So if we can find it at a very low level or at a very primitive level, we can go for proper treatment. As a result of the death due to this kidney injuries can be completely eliminated. So this can also be possible only if we can come with a reliable low cost sensing method, which we are proposing. Like we can use a HEMT-based device in order to attain this sensor, and this is again a reusable kind of sensor, so a person can use it at their homes itself, like in order to detect whether his kidney is having any problem or not. So again, we have tried for finding out the KIM1 sensitivity for this particular sensor if taken to a product development phase. So we are again finding these results, like we are comparing the results with the existing systems. So using our device design, we are attaining higher sensitivity compared to all the existing devices. So what I have to tell is like we have not come up with a very good device design. We have just used a simple device design, and even with a simple device design of AlGaN GaN Hemp, we are getting such high sensitivities compared to the existing devices. So if you can go for further simulations or further modifications in device design, obviously you will be ending up with a device that will be giving a very higher sensitivity or a higher sensitivity compared to our devices. So this research is still in a very primitive stage. That is, there are a lot to come in this particular research. So there is a requirement of large amount of sensors today, and HEMT is one such material. GaN HEMT is one such device that stands as a promise in this domain, like in the sensor domain, because its response time is very low. Like high frequency operation guarantees lower response times. So if we can go for modeling, or if you can go for developing a HEMT device that can be used as a sensor, then it will be a very big achievement, and we can use even the high power, high frequency domain devices for sensing applications, provided that fabrication is feasible in India. So this is a future work that we are planning. So we have fabricated the devices. So now what we are planning to do is, like, we are planning to develop some disposable gate cartridges. Disposable in the sense we are planning to develop some sensors just like the glucose sensors that are available in market. So they have those disposable cartridges on which we'll be applying a blood sample and we'll be testing the device. Similarly, we are planning to develop disposable gate cartridges, functionalizing it so that people can use this at their homes, so they can drop their blood samples onto the surface of these devices, which will be functionalized with prostate cancer antibody or prostate specific antibody. And then first of all, we are trying for this kind of detection to take it to the practical or clinical level. Like we are trying to use the sensors for prostate cancer detection. Further, what are the other things that can be done in this particular domain is like you can develop sensors for various applications such as physical detections, gas detections, chemical detections, and you can improve the sensitivity of existing devices also. For improving the sensitivity of devices, you can use a recess-based device or you can use an underlap-based device. Moreover, you can improve the quality of fabrication or optimize the fabrication recipes in order to get a higher performing device. So that's all I have to talk about the work I have done. Now, now I'm ready to
Bro, we are playing on pizza, dude. How much is it?
sir.
Yeah, but still.
Excuse me, sir.
You can continue, madam.
Sir, sir, I've completed my presentation. Now I'd like to like have the interaction session. Like I can answer if anyone is having any questions.
Thank you.